please take a seat. We're about to start the optical trapping and optical manipulation session. My name is Tom Perkins. I'm a fellow over at JILA, and my group uses optical traps extensively to study biomolecules. It's a real pleasure today to be introducing Kishan Dholakia, who is a world's expert in optical trapping and optical manipulation. Indeed, he's one of the program co-chairs for the upcoming optical trapping, optical manipulation speed meeting that happens starting on Sunday. So without further ado, I'd like to introduce Kishan, and he'll be telling us about optical traps, take shape, the role of multiple trapping, and beam shaping.
Thank you, Tom. Thank you for that introduction, and I'd like to thank Noel, Clark, and Yves Elliott for the very kind invitation to be here. I'm always enthused by talking to a completely different community because it always enthuses things that I've never heard of before, questions I've never heard of before as well. So I'm looking forward to a very engaging time here. So yes, my name is Kishan Dholakia, and I'm actually from Scotland. And unlike, I guess, people who live in the vicinity of this place, I live literally right next to the coast. So that scene is actually the coast, the beach at St Andrews, which is 5 minutes walk from the department. And for those of you who've ever seen the film Chariots of Fire, that won a couple of Oscars, I think, back in the 1980s, that was actually filmed on the beach then. St Andrews is an extremely small town. It's maybe only 15,000 people. But it's got a university that hopefully is getting better known in the sciences, but has a very strong arts faculty as well. And of course it is the home of golf. That and the university sort of keep the place ticking over all year round. So if you want to find any review papers or links to any trapping group, please look at our website. It should have a link to every trapping group in the world. If you have a group and it's not linked there, please let us know. And you can actually download and look at things on that website. So after thinking about what would be useful for this meeting, I know Eric Dufresne, unfortunately, because I was travelling yesterday, I missed his talk, but I've got an idea what he might have talked about, so I'm sure he gave you an absolutely excellent grounding in the basics of optical trapping and everything. What I thought I'd show is some examples, and I can only do some because of the time, of where things such as spatial light modulators and liquid crystal displays can actually impact in both fundamental science and new emergent applications in trapping. And hopefully there'll be something for everybody in this, and I'm very happy, of course, to take questions at the end. So what I thought I'd start with was to look at probably the two most popular ways of making multiple traps, or shapes. Because that's actually what you do with a liquid crystal device, or whether it's acousto-optic. What we might wish to do is create arrays of traps, more than one. And it engenders new science as well. It's not just doing 10 biomolecules versus one biomolecule, okay? It actually engenders new science and actually opens up new vistas in colloidal physics, dynamics of particles, and that's because optical patterns can be more generally termed as optical potential energy landscapes. We know that an optical trap is a beautiful example of it's probably the world's most elegant open damping harmonic oscillator at the microscopic scale, and we can understand it beautifully with undergraduate physics. But extending that allows us to look at tuning of interactions, for example, colloids, and actually looking at things such as surface chemistry, making adatoms and analogs to even atomic systems in ways that are very difficult to do otherwise. So we'll look at that. And then I picked a number of areas where spatial light modulator technology is I think, could be starting to force the pace. And at the end, I'll just say a few comments about where I think people who are interested in these modulators might actually concentrate some of their effort anyway. So I don't think I can skip this slide. So we already know this is a picture of how the trapping works in what's known as the Me regime. Trapping is actually largely experimentally led. In fact, it's only very recently this very elegant and precise theories are emerging how to understand an optically trapped object, right from the size scale of the Rayleigh regime through the Lorentz-Me regime, right through to the macroscopic size scale. And here's just an object that's trapped. If you'd like to go home and build one, there are many review articles. I'll just apply for one we wrote where it actually tells you what to look for when things go wrong. So it's got how you misalign the beam and all the silly things that you might want to overcome if you do that. The beautiful thing is it's a non-invasive, non-contact method. And this type of technique, of course, has opened up massive vistas and actually revolutionized single molecule biophysics. Until the mid-1980s, we looked at ensembles, but now we can pull, tug, twist macromolecules, study DNA, actin, myosin, kinesin, motional microtubules, and this can only get better and better. And the beautiful thing, as I'm sure Eric mentioned yesterday, is that you can actually do sensitivity down to the nanometers readily, and now down to the angstrom level, with something that's an optical technique. Okay, so that's one of the beautiful parts of this methodology. So this is just one of my students, postdocs, David Stevenson, loves graphics. So he was saying, we would maybe make these. You guys have lovely tweezing videos, but I don't like your animation. So he went away one night and did this. So this is just a trip down a microscope objective with a green laser. Through all the optics that they never quite tell you about when you buy them. Now David's involved. For the perfectionist, you probably would think the particle should be slightly above or below focus, but if you bear with me, it's to scale as well. It shows you a little object trapped and then maybe dragged away in a capillary. And that's the sort of thing you can build readily if you go back home and onto your microscope or a home-built microscope and maybe take it away for further study. But why would you like to make multiple traps? Why on earth can't I just live with one or two and do my beautiful force measurements? Well, there are many reasons. One is obviously multiplexing. Another very nice reason is looking at colloidal interactions that can be solver-mediated, looking at the potential, and actually mapping out what's actually happening to colloids over a large region. We can control colloids inside their terms of their surface chemistry, their polydispersity, maybe charge. That's another thing you can do. We can also actually start to understand competitive effects, for example, in things such as what, for example, Clemens Beschinger does, for example, between these sort of electrostatic interactions and landscapes. And more interestingly as well, from my point of view, you can actually start to investigate the light field itself. Optics is not as well understood as some people might think. There's some very, very elegant new light fields that are emerging, which actually have beautiful intrinsic properties that are challenging the way we think about the propagation of light, the focusing of light, and optical tweezers can act as beautiful probe particles to do that. So I don't just want to make an array of traps. I might wish to actually sculpt the face front of the light field as well. And I might wish to combine this and then probe that with my test particle. And that's what these multiple traps can offer. Okay, so these are some of the things that we might want to do. So there are obviously quite a few ways to make multiple traps, and I apologize for those of you who use galvanometers or interference-free light beams. Some of the work I think Noah Clark did in the mid-1980s on laser-induced freezing was with interfering light beams, if I recall correctly, which is one of the first examples, I guess, of multiple traps and looking at structure factors of colloidal aggregation. At the moment, these two are the two most popular ones. This is the one, obviously, I think will interest most of the community, which is the spatial light modulator, which is an array of liquid crystal droplets that we can electrically or optically address with some AR coating and sculpt the face front. The one that's probably been around a lot longer, and is still very useful indeed, is the acousto-optic deflector, which uses a sound wave to diffract the light extremely rapidly. The reason we can actually scan the light extremely rapidly is, of course, because if you go back to the Overdamped simple harmonic oscillator idea, if I have a trapped particle, it's rather like me in a swimming pool. Unless I'm an Olympic swimmer, I can't really move very far. So in fact, the diffusion time is extremely small for objects, say, a micron or so, and so I have time to whiz around and come back and actually grab myself again. So here's a video with an acousto-optic, so the other side, just to show you how that actually works. This is acousto-optically done, so to spell my name, it's actually speeded up, which you can tell from the sort of Brownian motion. And incredibly, it's like the most expensive word ever. Now, this is actually a bit spooky when someone told me this, but actually my name is an anagram of Arthur Ashke, because I think I was like one or two when he was starting thinking about this. So, anyway, if you believe in some divine intervention, anyway, there you go. So we thought that would be a fun video to make. Now, of course, you can do that with the SLM as well, but that just shows you that you can do pretty amazing things with acoustic devices as well. Why can I get away with that? Let's just put some, for students, these are beautiful little calculations and problems you can do. So if you look at the Einstein diffusion coefficient and look at a simple idea of a diffusion time and then take an object, say in microns, and you say maybe my tweezer is away for 25 microseconds, then I only diffuse 5 nanometers, and maybe I can live with that. 5 nanometers, unless you're doing some very nice, precise biomolecule study, you can probably say I'll get away with that, and it's okay. So that tells you some kind of accuracy you can get to. Of course, the beauty about spatial light modulators or static diffractive optics is instead of time sharing, I fan out the light beam in a way that I decide to do. Why can I do that? Well, here's just the reason why these things work in a simple diagram. Here's a normal trap will come along here. If I want to make a trap just adjacent to it, it is equivalent to me making a little glass prism and sticking it on the back of my little microscope objective. Of course, I'm not going to do that, but what I'm saying is if I introduce the appropriate phase delay, I can do that. Another very simple example is the Fresnel lens, which looks a little bit like that thing when you see a Warner Brothers cartoon. And that allows you to focusing up and down along the axis. And that's really in a nutshell what a spatial light modulator can do in sort of basic configurations. It can do more or less any of these things very, very quickly. Not as quickly as the AOD in some respects, but its refresh rate is one of the things that people do discuss. There's not really a huge optical trapping experiment I've seen that's been limited by refresh rate, but of course I stand to be corrected. But as an aside, many people are starting to use these in Bose-Einstein condensation studies and developing optical lattices, where many of you know that you want to make low-dimensional quantum gases and actually look at things such as Mott-insulator transitions. Now there, of course, we do need fast refresh rates, so that's something where maybe ferroelectric SLM could be the answer. And a couple of groups have already started doing that, just as an aside. Anyway, using a number of algorithms, the Gertzberg-Saxon is a popular one, we can actually take an input beam and either in first order or in zeroth order create a holographic image through a lens. It's a very poor choice of colour for me there. Here's an example from a paper by Eric Dufresne and David Greer in 2001, showing where you place it. Here they've got a static diffractive optic, not a spatial light modulator, but the physics is the same. The optical train is more or less the same where you place it, conjugate to the back aperture. So these 2 points like pivot around each other, and so we don't lose actually going in through that objective. And here's the DOE that they patterned, creating this array of traps. I'll just comment, there are other techniques as well that are very powerful using spatial light modulators, which I won't have time to talk about. And one of them is the direct phase contrast technique by Jesper Gluckstad and colleagues, which is equivalent to sort of something like phase contrast imaging as introduced by Zernicka, where there's a phase correlation right through to intensity at the trapping plane. Now, at the moment, that does offer rapid computational advantages, if that's what is an issue for you, and that's something if you want to go and read about, you can. And there are other techniques like bringing in the Fresnel domain, which Burnett and Monica Rich-Marta actually do, which also is very nice, and you can basically use the SLM rather like a display there. Anyway, let's start talking about some applications. So one of the nice applications that emerged from a couple of groups about 5 years ago was the concept of optical sorting. So optical sorting is the ability to actually separate objects based on a physical characteristic, in this instance without actually using a marker. So of course we can have something akin to a fax machine, a fluorescence activated cell sorter or something, where particles come along and I drag them out. Now imagine I could tell you could somehow use a light pattern to distinguish objects just based on their size or their shape or their refractive index. How might that work? And why might we use multiple traps? Here's my particles in the multiple trap array, rather like eggs in boxes. And this is a reasonably popular game, I guess, at this side of the Atlantic. Clinker. And what one finds is that, so what I'm doing here is basically taking my egg boxes and lifting it up, alright? And I'm going to watch the eggs roll. Now, of course, we've got to think about Brownian motion, diffusion. We've got to think about the pattern and the response of the object pattern. So you can see here, this object follows, if you like, a statistical path, whereas this one's more deterministic. In other words, I'm always sure the little ball's going to end up in that object, in that little gap 2 there. Okay, now let's think of another lovely physics analogy to actually look at that. So imagine I have 2 balls at the top of a roof. Okay? I roll the little one down, it stays in the grooves. I roll the big one down, it stays in the grooves. I now tilt the roof. I roll the little one down, it goes up at an angle. And the big one, well, it might not take as smooth a trajectory as you've just seen, it does that. So this is exactly, or more or less, how optical sorting worked, whether done acoustic-optically by interference or spatial light modulators, where particles can follow in commensurate directions to my optical landscape. Here it's just so the roof is the light. Alright? Microfluidic flow replaces gravity for me, and these are the 2 objects that I might wish to sort. Okay? You obviously want to see this working, so these are some papers that you might go away and look at, including a mixture of theory and experiment. So on the top right, this is my idea of the geometry. On the bottom left, these are all real-time videos. And this is, the beautiful thing is multiple traps are taking, there's nothing really trapped here, you know, it's just deflected. Alright? And that's why you get a much, much higher throughput, which is exciting lots of people in the domain of microfluidics and lab-on-chip sort of examples. Here on the right, you see a light pattern that my colleague Thomas Sismar will be discussing tomorrow that we've worked on, which is just a set of concentric rings, and it's not a propagation invariance, it's vessel beam. And it's actually sorting red and white blood cells without the adding marker. And that's because, if you know a little bit about biology, white cells are spherical with a nucleus, okay? And erythrocytes and lymphocytes are biconcave discs that can flip up and respond differently to my potential energy landscape. The physics is very similar. Here you see a clump of white cells just collected there, without any marker. Now this sort of technology is there's many hybrids now of this variant of this work out there. There's a lot of people actually working on it, and there's a lot of people interested to see how far you can push this technology. But again, a very exciting area for multiple traps. Now let me talk about something that I'm not involved in at all, but it's work of David McGloin and some other colleagues. A lot of work is being done in aerosol chemistry. This has been an emergent technique in the last 2 years where people would like to understand what's actually happening in droplets. People are thinking of droplets as, if you like, carriers for single cells or viruses and molecules, and people would like to understand fusion and reactions actually happening in single droplets. And tweezers can actually add a lot of advantage here. So here, in this paper, David and his colleagues are actually looking at manipulating single droplets with a spatial light modulator using a nebulizer in an oversaturated atmosphere with salt, actually fusing droplets together to look at multiple reactions. And here's a video of from one of the, I think it's from that paper. And here, instead of solid polymer particles, you should see, there we go. So these are 4 droplets held by a spatial light modulator, and then by tuning it, so you can see the amazing advantages here of what you can do. You can isolate a droplet from its environment and maybe have it react and do surface chemistry. So a lot of chemists are getting very excited by this type of technology to do that. Okay, again. So droplet chemistry is obviously very interesting for environmental scientists as well, but it's a very nice and emergent use of the spatial light modulator. So I'm going to talk about one light beam, but it's not this one. So this is the one you hear about from Thomas Sismar. We've done a lot of work on this. This is the Bessel light mode, or the pseudo non-diffracting light mode. Basically, the interest in this one is because it doesn't spread as it propagates. This is just a white light version of it, maybe with a super continuum, but I'll leave it to Thomas. If you want to hear more about this beam, it's done with spatial light modulators with applications in trapping and biophysics. Please come along and see his talk tomorrow, which I think is at 3. What I'm going to talk about, though, is a different light beam. So, colleague Grover Schwarzlander, who works at the University of Arizona, kindly lent me this very nice pastiche he made. And it's actually in the area of phase singularities. Okay, so I don't need to explain what you're looking at here, especially to people on this side of the Atlantic. But here you see the emergence of what we call a vortex. Okay, a singularity, if you like, due to turbulence here, creating, if you like, the eye of a hurricane. Now, vortices are ubiquitous in nature. You read about their superconductivity in fluid dynamics, etc. Optics is no different. Optics is no different, okay? And the beautiful thing about optics is it's a lot easier to study them and safer than actually studying something like that. And so this is one of the beams that I will describe to you, where instead of any airflow around the singularity, of course, we have a circulation of intensity and a phase profile around there. Now, vortices come in many guises, and this is one of the most popular ones, which was really, the field was instigated by Les Allen and colleagues in this paper, if you want to look at it, in Physical Review A, which is the Gauss-Laguerre mode. So it's an optical vortex. Essentially, this beam is a TEM00 mode. If I wanted a higher order mode, what I'd actually have is something that would be known as a Hermite-Gauss illusion. Would have Cartesian symmetry, in other words, numbers of lobes in 2 dimensions with nodes. Now, this is exactly the same. It's an orthogonal basis set for laser modes, and the reason you don't normally see it coming out of your laser is because it's something like a Brewster window or something that destroys the symmetry. But this is a very beautiful beam, very, very useful in numbers of studies, even including droplets, which I won't go into. But of course, this is beautiful to make with a spatial light modulator because it allows you, it's a very, very easy way to configure between different versions of this mode. The P index tells you how many, P plus 1 tells you the number of annuli. And this L index just tells you the number of cycles of azimuthal phase that you accrue as you go around the mode. It's rather like a spiral phase round, okay? And because of that, it has very interesting properties, as you can see here, with a corkscrew-like motion of the pointing vector, that then gives you an azimuthal component, released a type of angular momentum that is not the same as angular momentum associated with photon spin that we normally see. So let me just show you some examples of that. For those of you interested, this is how you describe the mode. The main things to look at, it's actually just this term that really you want to keep your eye on, e to the I alpha. That's really what it is, an azimuthal phase term. That's the Boy phase of the beam, and the rest, I'm sure, is reasonably explained. That's the associated Laguerre polynomial. And these are the form of the helix. And in fact, it's rather like a pasta spiral. So next time, I don't really call this pasta over here, but it's rather like these little pasta spirals you get through. Next time you're buying pasta, you might want to think about that. It's very similar to double, triple star helices. Here's a hologram that you get on your SLN, and it's a phase reference to that. It's not a phase discontinuity, right? That's 2 pi or 4 pi. And why is it dark in the middle? This diagram explains it. Because all of these points, just like a ramp, if I was walking around a spiral staircase, they all meet in the middle. They all meet in the middle, they all destroy each other. So this beam gives you a perfect darkness. A really, really good darkness. It's a much better darkness than putting a little black spot of ink on a glass slide and putting in your laser beam, because diffraction fills that. This is a real darkness with this optical vortex. Okay, so what type of things might we do? We can actually transfer this twist or this helicity of angular momentum to objects. Now, that can be due to, if you like, a ramp, so it's going to be due to the process of scattering. There's also the spin angular momentum I haven't discussed, that we know with light, and they can be decoupled or added. Spin, of course, we know is changed by birefringence. Why do I say that? Well, we all know a waveplate will change the polarization of light appropriately. And OAM is actually analogously affected by what we call astigmatism. So why would we want to do rotation or twisting or mixing? Well, as I'm sure all of you know, we're working in what we call the low Reynolds number regime, where basically viscous forces dominate, we can't rely on turbulence. The things that mix or twist or add up objects are very, very good. So a lot of people at the moment are using these for things like microrheology. By spinning an object, get into a terminal velocity, and balancing against a torsional Stokes drag, you can actually measure local viscosity inside a liquid, maybe inside a cell. That's something one might like to do. You can actuate elements for lab on a chip or look at hydrodynamics. Okay, so there are now I should say there are lots of eminent groups looking at liquid crystal physics as well with optical tweezers. We're not one of them. This is our very small foray into that, which was just to spin a liquid crystal droplet. So here's a liquid crystal droplet spinning due to birefringence. It's acting like a microscopic half-wave plate, because of course, as we know, if you pass circularly polarized light through a half-wave plate, regardless of its orientation, the velocity of rotation of the ether vector will reverse. And that leads to an exchange of 2 h-bar, from this very simple equation, with the object. Now people are actually using not really liquid crystals, but crystals of materials such as baterite to spin objects very, very quickly, and then balance that against a rotational Stokes drag, which has a component of viscosity. And I can certainly point you to groups who are doing that. Sometimes you can't get birefringence though, of course, but not everything's birefringent. We're limited to a very small number of materials, and what we might want to do in the microfluidics community is actually actuate cogs. Well, you can actually use your knowledge of photonic crystal to imprint or force something to be birefringent. This is a real cog manufactured at St Andrews made from a polymer known as SU8, where we've just put a ribbed line through there, and that's actually equivalent to a 1D photonic crystal, where the light basically sees a different refractive index going along the lines or across it. If you don't do that, then you get away with having to worry about getting baterite or a liquid crystal. What you actually can do is hopefully make something like this. And if my computer goes, there we go. So they have 2 cogs held and spun with line, and then just throw them away. You let go. Now, if you're really into this field, you probably know that the optical pumping rates are ludicrously low, and it's actually not a really viable technology. But it's key science, and it's actually could be useful, probably not for pumping, but actuating. In other words, actuating a valve or something. There, I think there's a lot more advantage. So I'm not going to sit here and sort of tell you you'll go home and make a pump with optical tweezers, but certainly actuating devices could be a very exciting way to go. Here's work of David Greer and colleagues, for example, using those optical vortices to, in fact, and what you can see here, why are the particles spinning? Remember, they're going around a spiral round due to scattering. And he's using arrays of these, creating holographically with a spatial light modulator, to actually try and pump particles around. And also, you should look at the work of Monica Richmada, who's also done similar things using spatial light modulators for pumping. You can even understand fundamental physics. So there was a lot of debate in this community about the coupling or decoupling of spin and orbital angular momentum. So the photon spin versus how a photon can actually accrue this azimuthal phase turn. So here you're seeing objects in a vortex beam that are spinning on their axis because they're birefringent. The light feels circularly polarized, but they're going round and round. So we're decoupling spin and orbital angular momentum for the first time. And this is something that was very exciting, again, accentuated by the idea of holographic systems and holographic traps. So, in the sort of 5 or 10 minutes that I...
8 minutes.
In the 8 minutes that I actually had up to, I'll just tell you about some fun new directions using spatial light modulators that might be of interest to people. So, this is a really simple experiment that I'm sure everybody's had a go at and read the final lectures on, etc. It's a double slit experiment that embodies everything about quantum mechanics, okay? So I don't need to explain now what you might see. What you might be surprised to know, that even just putting a vortex actually onto 2 slits like that actually gives you something rather unusual on the other side. It's a very nice work of these people here, Stoll and Alfano, if you want to have a look at it. Okay, and also the work of Soskin as well, I think, has done something similar. So this is something I'm leading up to using white light in optical trapping, which is a new kind of area that's emerging at the moment for a number of reasons. So here we have a super continuum source. So for those of you that don't know, there's a new generation of more or less white light lasers that use ultra short pulses and photonic crystal fiber to disperse the light and create not uniform amplitude, but certainly very high power broadband light sources. White light is extremely useful in biophysics and for low coherence interferometry, which is a very emergent and powerful way. OCT, for example, some of you may have heard of, is uses sources like this. Spatial light modulators, if you buy the right ones, you can more or less encode onto white light. Here, what we're doing is we're actually seeing if we can encode and make Gauss-Laguerre beams of white light, and here you see them up to order 10, so that's 20 pi if you go around the ring. So it's a very, very steep azimuthal phase. If you do the young slits experiment, what you find is because of that azimuthal phase and then the slits sampling it, if you actually plot and compute what's happening, the slits actually allow you to calculate actually turn into these sort of skew lines. And the shift in the number of fringes is actually related to the azimuthal index, which is a very, very interesting piece of acute optical physics. It's a very, very nice way of doing that. This is just to show you that the white light fringes are actually there. This is actually a computer model for that. Why am I showing you that? Because we then went on to look at optical trapping with white light. So, one thing I should say is, why would you want to use white light and optical trapping anyway before you look at all this? Well, if you're doing trapping and spectroscopy simultaneously, for example with droplets, this is extremely powerful. Okay, it allows you multiple wavelengths to sample your trapped object at the same time as you're trapping it. With a supercontinuum and bandwidth filters, you can actually do both at the same time. Also, white light also allows you to remove effects of interference. I don't have time today, but I'm hoping Thomas will actually show you a new kind of trap with photonic crystal fiber that we've created that actually removes interference. In other words, if I'm trapping a lot of objects, okay, interference, scattering right from one object will dictate the equilibrium position I sit at and vice versa. And that means that if I'm trying to compute the potential energy or the topography of where everything's sitting, it's a very complex problem. When we've done, Thomas hopefully will now slip this in, given what I've said tomorrow. But that's just one example. Why did we do vortices with white light? Well, if I would make a white light beam circularly polarized, that's not so easy. I could use one of these Fresnel longs. But the beautiful thing is with a spatial light modulator and an appropriate phase shift that actually accrues for all the bandwidth, I can actually impose orbital angular momentum over a very large region. Okay, that's my computer deciding to. Okay, I'm going to very quickly just skip just 2 minutes just to say something about nanoparticles. So I know Tom here has done one of the nicest papers in the last 5 years on nanoparticles, showing I think that there was temperature changes of 266 degrees per watt or something. So nanoparticles are very exciting because they're part of plasmonics, they're useful in imaging, biophysics. Why might we want to use SLMs or beam shaping? Well, one of the things that I'm actually a quantum physicist by training, and I used to work a lot of time making what we call blue and red detuned traps for things like atomic ensembles. And I was always wondering whether we could actually do something similar for a nanoparticle, because it's got not a very sharp resonance like on a dipole transition, but it's got a plasmon resonance. And the idea here is that everything you've seen at the moment is for dielectric objects, where we understand we've got bound electrons, we know the index of refraction. You have to play games and you can get something known as a plasmon resonance, which then means we can actually compute the polarizability and the scattering force around them. This is something that will be very interesting. If you do that for gold and silver, you get some very interesting properties. For example, with gold, if you do this, you actually find, this is where most people have trapped nanoparticles, I guess, somewhere up here. That's the polarizability. And polarizability is essentially what tells you how well it's trapped due to gradient force. For dielectric objects, you can say it's proportional to volume. But if you go near, say, the plasmon resonance, you start seeing changes in the polarizability. You also see huge changes in the scattering and absorption as in near any resonance. And this is when most people operate. But if you operate here, you can actually get that to dominate. So, well, sorry about this, but given time, if you use holographic trapping, you can create a dark trap for nanoparticles near the resonance. Okay? This is going to be done with SLMs, or this is the fault hologram that we have there. And you can actually trap particles in the dark region. This is slightly inspired by Tom's work, where he showed huge temperature changes. If we can actually cage nanoparticles in regions of darkness, this could be quite useful for actually people looking at maybe plasmon pairs and actually other studies. So that's what we did. Here this is the particles caged. It's not really technically trapped extremely strongly, and this just shows you the resonance time for that. Yeah, maybe I can show you a quick movie to end. But maybe not. Now, we've actually plotted the particle lecture is actually a lot more interesting than you can see. It makes actually a little bit of hair. If you can just keep your eye on it. which is actually interesting for another reason. But this is just, again, another example of something that will be, I think, a big area with multiple trapping in the future. So I'll stop there. I hope in this very short whistle-stop tour I've shown you why we might want to optically beam shape and actually create multiple traps with spatial light modulators, and shown you a sort of variety of examples. There are areas where SLMs could, of course, be improved in terms of maybe some areas of pixelation, diffraction efficiency, refresh rate, etc., and maybe large power handling. But they've really come on leaps and bounds that people are finding new applications, examples of droplets. And also they're very much being used in multiple modalities in microscopes now, also in biophysics. So I think it's a very exciting time for the community, and I'm happy to take questions. Thank you.
Any questions from the audience?
So, Kishan, I was wondering if, in the last example, or more generally, you thought about the. So we always talk about optical trapping when we have focused laser beams, but you talk to a lot of people in chemical engineering communities, and they talk about this phenomenon called thermophoresis, and that's the point. That's something called the Sorey effect.
Oh yeah, the Ludwig Sorey effect.
Yeah, exactly. And so what's interesting about the sorts of thing you showed. It's difficult. I think it would be difficult to disentangle, right away what's coming.
Yeah.
The simple question: can we use thermophoresis together with optical trapping?
Yeah, that's a good question. Okay, so some groups have done this. I mean, an experiment I didn't show is we did some work on evanescent traps with surface plasmons, where you can look at convection, all right, and you can then, by carefully tailoring the sample chamber, you can actually induce thermophoresis. Now, I think it's Alba Lipschitz had a very nice paper in 4 years ago talking about the competition between thermophoresis pushing from hot to cold, convection, trapping objects, all right, they're DNA rings. Now, you're right, we could look at the competition, but what I sense is that thermal forces usually vastly swamp the optical component. So when we did that experiment anyway, that particular geometry, we had to work very hard to say this bit was optical. In other words, we saw this thermophoresis versus the convection, and then we saw some alignment due to the optics. So yes, you could do it, but I imagine most geometries you'd have to mostly think about the thermal side and the Ludwig Sorey coefficient for all these objects. But it is an interesting area, I agree.
Okay, up in the back.
How do you avoid the chromatic aberration?
Sorry? The chromatic aberration? Yes, that's a great question. Okay, so the honest answer is we can't, and so for those of you who... We can mostly compensate here. You see this little element here. What we wanted to do really was create large areas of traps actually, and we found it was extremely hard even to create two and compensate with a prism. Now I guess you could maybe use another spatial light modulator or some other trick to do that. So this prism basically was designed to help compensate, but we haven't attacked that problem for larger arrays, and that's a very good question. But we haven't got a great experiment to do with multiple light trap arrays, so we sort of left it at that point.
Okay, well, I have a question. So,
Sure.
For droplets, I mean,
Yep.
two different classes of experiments with droplets are droplets and aerosols, and droplets now in either very low index stuff like Chris Thomerson's group,
Yes.
or oils. So of these sort of three different droplet technologies, do you have a favorite, or one you think that's gonna?
Right, so firstly, I don't work in this area, so you're right, Chris Helmerson works a lot, a guy called Daniel Chu in University of Washington, and David McGloin. So I don't work with this, but I will say you need different geometry. A good example is if you're doing droplets in oil, what you really have a low index particles. So there, for example, what they've done, and this again is a good example of spatial light modulator technology, they've used two optical vortices and trapped them, and they come together. And then they say, oh my god, the optical vortices are actually going to stop them coalescing. So then what they do is they actually move the vortex, the hologram slightly off axis, so the hologram goes from circular to sort of crescent shape, and it allows the material to fuse. Now, as to what experiments you do in each geometry, I'm not an expert, so I will pass that over to somebody who knows a little bit more. I guess this is more for sort of atmospheric chemistry. The surface stuff is more for sort of people who do microfluidics and single droplet reactions and maybe try and encapsulate a cell or a virus and really look at control. People who want to look at, say, single molecule threat, for example, and that's obviously what you wouldn't do with the system David stuff, but might do with maybe something Chris Helmerson's done, I guess.
Any other questions? If not, let's thank